So now that we've learned how to take measurements, what units we use, now we're going to learn how we can take those measurements that we have gathered and use them. Okay? So the first thing we're going to talk about is precision versus accuracy. When we talk about precision or accuracy in our everyday lives, people oftentimes use those words to mean the same thing, right? If they're describing someone who's precise or someone who's accurate, they usually mean the same thing. But in science, they have two separate meanings. If you're talking about something being accurate, you're talking about how close is that measurement to the correct or accepted value. So for example, if something actually weighs 5 pounds and you measure it to weigh 4.99 pounds, you are pretty accurate. If you measured it to weigh 3.78 pounds, you would not be accurate. You are significantly different from what the actual weight of the object is. So if you are comparing accuracy, you're saying, how close am I to the actual measurement? This is limited by human error. Okay, so did you use a tool incorrectly? Did you make a mistake copying data? Did you measure something, like weigh something incorrectly and then not throw that measurement out, right? So accuracy, how close you are to the actual real value of something, and it's determined by, did you do this correctly? Did you measure correctly? The other side of the coin is precision. Precision is how exact was your measurement. Okay. Did you measure something as being 5 pounds, or did you have a scale that can actually tell you decimal places and you measured it to be 5.79 pounds? That is more precise. You have more data on exactly what that weight is. Okay, you're not just getting the ones place, but also the tenths and the hundredths place. This is limited by your measuring device. Okay, there's no way you can affect how precise a measurement is. It all is determined by your tools that are available to you. If you only have a ruler that has markings at every inch, you can't be more precise than a whole number of inches. But if you have a ruler that is measured is a meter long and it measures meters, and then it also has markings at decimeters and centimeters and millimeters, now you can say something is one, let's say it's 37 millimeters long, right? That's more precise because you can go out to more decimal places. Also, precise measurements, if you're taking measurements precisely, they're going to tend to be grouped close together. You're going to have similar measurements over and over. I included an image in here to help understand this, okay? And it's this image of the 4 bullseyes, right? If something is highly accurate and highly precise, it's going to be like the first bullseye. It's accurate because we hit the bullseye. The bullseye is the accepted value for this, and we hit it dead on. And it's precise because all of our measurements are right in there, close to each other. They're grouped together. If something is low accuracy but high precision, you'll notice that all the values are similar to each other. They hit in roughly the same spot on this, but they didn't hit the actual target, right? They didn't hit the accepted value. They didn't hit that bullseye. Something can be highly accurate, so hitting the bullseye, but low in precision. Your data's kind of scattered all over the place. And then you can also have the last one, which is the one we want to avoid if at all possible, which is where your accuracy is low and your precision is low. Your data's kind of scattered all over the place and it's not hitting the target, not hitting the actual measurement. Then we shall move on to percent error. So if you have an actual measured value, like the book gave you the actual value of density for copper, then you can calculate your percent error, or in other words, how far off target was I. Your percent error is going to be your experimental value minus your accepted value. Then you're going to divide that by your accepted value and multiply by 100. If your percent error comes out as a negative number, then that just means that your experimental value was below the accepted value. It was less than what the accepted value is. If your experimental, or if your percent error comes out to be a positive number, then you know that you overshot. Your experimental value is higher than the actual value. Now let's talk about significant figures. Okay? Significant figures are how you tell other scientists which numbers that you're reporting you actually measured and know for certain, and which ones are estimated. There are rules for determining which figures are significant, and I have provided you with a handout, which is what you saw on Google Classroom. It's called Rules for Significant Figures, and we're going to go over them. But before we do, I'm going to show you a video. So, now that we understand why we need significant figures, here's how you can look at a number and determine how many significant figures they are reporting. Okay? First things first, all non-zero digits are significant. We don't use numbers like 6 and 8 to be placeholders. So if somebody is reporting those numbers, it means they measured them and they know them for sure. So any number that has any non-zero number in your number is significant. So 1.234 has 4 significant figures. There's 4 non-zero numbers. Okay? Any zeros that are between 2 non-zero numbers are significant. Because if they're between the two, then you know they measured further than those, and so you know those zeros are significant. So 1002 has 4 significant figures. If it was just 1000, we wouldn't know if they had measured all the way down to the ones place, but because it's 1002, we know they did. So those zeros in between are significant. Zeros that are to the left of the first non-zero digit are not significant. So they're just a placeholder. So if you have 0.001, those zeros that are to the left are not significant. That they are just holding the decimal place for you. The 1 there is the only significant number, so it is 1 significant figure. If there are zeros to the right of a decimal point in a number, and they are after a non-zero digit, then they are significant. So you can see there that 0.023 only has 2 significant figures, because that 0 comes before the non-zero numbers. But if it comes after, like in 0.200, we assume that they have measured out to that place and found a value of 0, so they are significant. So you can see why it's important not to just leave placeholder zeros on the ends of things. Because what you're telling another scientist is, I measured it and I know those are 0. Okay? And when a number ends in zeros that are not to the right of the decimal point, those zeros are not necessarily significant. 190 could be 2 significant figures if they didn't measure that last digit, and it could be 3 if they did measure it. So you can do one of 2 things. You can either put a decimal point there at the end of that number. So if it was 190 point, then you could say that that 0 is significant. Or you can put it in scientific notation, which is the preferred method and the method you will see me use a lot. So if they put 1.90 times 10 to the second, you would know that that 0 is significant, because if they included it after the decimal there in scientific notation, it's a significant figure. So the other example they give there, 50,600 calories, could be 3 or 4 or 5 significant figures depending on which place they measured it to, and they can indicate that by including those zeros or not including them in scientific notation. So if they just wrote 5.06 times 10 to the 4, that tells you that they only measured 50,600, and they didn't measure those last two places. They didn't measure the tens or the one spot. So they're not significant. They were placeholder zeros. But if they put 5.060 times 10 to the 4th, then that tells you they measured 50,600 and something. So they measured that zero there was actually 0, but then they didn't do the ones place. And then just like that on the last one, if they write 5.0600, then they measured all the way to the ones place. It was exactly 50,600. It wasn't 50,601, and it wasn't 50,599. It was 50,600 on the dot. That's what that means. Let's talk about exact numbers really quick. When you're going to deal with exact numbers is usually as a conversion factor. Okay, we know there are 100 centimeters in a meter. That's an exact number. So when we start to do math, you don't have to factor those into your significant figures because they're exact numbers. Okay, so you don't have to worry about should my answer have two significant figures because I used a conversion factor that had 10 in it. You can ignore them in terms of calculations. All of this will make more sense when we do practice problems with it, which we will do tomorrow.